Hi, welcome to Lesson 10.6, Segment Relationships in Circles. Now for today's lesson, we're going to need to be using a quarter of a sheet of paper. So on page 303, grab a half sheet of paper and cut it in half, and go ahead and glue that on top of page 303. Okay, so pause the video, do that, and then restart it again. Now on the next page, on page 304, you're going to do exactly the same thing. Okay, a 1/4 of a sheet of paper, glue it on page 304. Now, on the next page, 305, I want you to grab a half sheet of paper, and I want you to glue that horizontally right on top of page 305. So go ahead and glue that whenever you get a chance. Now, at the bottom, we are going to do example number 1. Now, there's a series of theorems that we are going to go over today, and I will explain a couple of them. Now, the first one is the segments of chords theorem that states that if two chords intersect in the interior of a circle, not necessarily in the center, because if it's in the center, then they're all radii. Then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. In other words, EA multiplied by EB is going to equal EC times ED. And we're going to be looking at why it is that is true. Okay. All right, so on page 306, okay, everybody go to page 306. We are going to be doing problems 2, 3, and 4, as you guys can see right there. All right, so let's look at a little bit of vocabulary. A tangent segment is a segment that is tangent to a circle at an endpoint. Okay, so this right here is a tangent segment. A secant segment is a segment that contains a chord of a circle. So this right here is an external secant, because it contains part of a chord, okay, and has exactly one endpoint outside of the circle. The part of the secant segment that is outside the circle is called the external segment. External segment. The segment of secant theorem. If two secant segments share the same endpoints outside of a circle, then the product of the lengths of the one secant segment and its external segment equals to the product of the lengths of the other secant segment and its external segment. Very confusing wording, but all it really means is that the product of this segment right here multiplied by the whole segment right here is going to equal to this segment right here multiplied by the whole segment right there. Okay? So we're going to be looking at that. So look, EA multiplied by EB and EC multiplied by ED. And we're going to be looking at why that is true. The next one is the segments of secant and tangent theorems. It states that if a secant segment and a tangent segment share an endpoint outside the circle, then the product of the lengths of the secant segment and its external segment equals the square of the lengths of the tangent segment. Very wordy for the following. Okay, so if you have an external point, you have one that is a tangent and you have one that is a secant segment, then this length right here, okay, EA squared is going to equal to the product of EC times ED. And we're going to look at why that is true. Okay, so once again, 2, 3, and 4. All right, let's go back to page 303, and we're going to be using this diagram to demonstrate one of the properties or one of the theorems that we were just looking at. Okay, so what you have here is you have two chords intersecting inside the circle. Now what I'm going to do is I'm going to create two sets of triangles. Okay, as you guys can see right there. Now, one of the things we need to remember is that these two are intersecting lines. So this angle right here is going to be congruent to this angle right there. Now, I know it's probably a little bit difficult to see, but this angle right here, this one right here, angle E, is going to be 1/2 the measure of arc BD. Okay, and for the same reason, because angle C, okay, because angle C shares that same arc, angle C is also going to be 1/2 of the distance of this arc, which means that this angle and that angle are going to be congruent, okay, because they both have the same intercepted arc right there. Now, when you step back and look at these two triangles, you're going to notice that they have two pairs of angles that are in common, which means that by angle-angle similarity theorem, the two triangles are going to be similar. Therefore, they're going to be proportional. Okay, so that is what we're going to be looking at. Okay, so BF, segment BF, this one right here, is going to correspond to segment FD. Okay, so BF is going to be similar to segment DF. Okay, so this is to this, okay, as EF is to CF. Okay, just like that. Okay, so now what's going to happen is that you can cross multiply and get the following. BF multiplied by CF equals EF multiplied by DF. So therefore, we can now see that the product of this segment times this segment equals the product of this segment times that segment. And this one right here, this is the segment of Chords Theorem. Whoops, let's go up a little bit. All right, so this is not like a formal proof. We haven't done it to a 2-column, but this would be the framework for explaining why this works. All right, let's take a look at the next page. Okay, now this one looks complicated, but it really is not, okay? So this is the actual segment of secant theorem, okay? This is the one that's going to state that this segment multiplied by this segment equals this segment multiplied by this segment. Now, how are we going to do this? Well, first off, I'm going to connect, let me get a protractor and make this a clean line. I'm going to connect C and F. Okay, I am also going to connect E and D. Okay, E and D. Now, one of the things that we have to look at is that both of these triangles right here, this one right here, and this one down here, they both have a common angle, which is angle B. Okay. Now, one of the things that we have to look at is the fact that my mechanical pencil is no longer working. There it goes. Okay. Is that both of these angles right here have the same intercepted arc. That one right there. Okay, so just like in the last problem, this angle right here is going to be congruent to this angle right there. Okay, so therefore you have two triangles that happen to be similar. So I know it's a little difficult to see them. So what we're going to do is we are actually going to separate them. Okay, so we're going to be separating the top one. Okay, and they're not going to be up to scale. That's okay. Okay, so I have B, I have C, I have F, one arc, two arcs, and then I have the second one, looks something like this, B, D, and E. Okay, 1, 2. So by angle-angle similarity, both of these two triangles are going to be similar. All right, so therefore we now have segment BC, that's this one, proportional to segment BD. Okay, and we also have BF proportional to segment BE. Okay, so when you cross multiply, you're going to get the following. You're going to have BE multiplied by BC, and that's going to equal the product of BF times BD. So when you're looking at the original figure, okay, this is basically what you have. You have BE multiplied by BC, and that's equal to BF multiplied by BD. And that is why the segment of secant's theorem works. Okay, so take a minute and finish writing that down. Okay, this one's a very easy explanation. The next one is a little bit more complicated, so bear with me on that one. Okay, in the next one is for, let me give myself a little space here. The next one is for the secant, no, not secant, segment of secant and tangent theorem. Okay, so that's that second one. Okay, now we say that we're going to have two different cases. So the first case, let me go ahead and draw my circle, okay, is where you have an external point tangent to a point on the circle, okay, but in this case, that secant, what do you call that, the secant chord? Secant chord, let me get my vocabulary right. Secant segment, sorry. The secant segment is actually going to go through the center. Okay, that's why it's called case 1. Okay, in the second case, we are going to look at what happens when it does not go through that. Okay, so you have an external point, and it just goes through anywhere that is not the center, because it either goes or it doesn't go. Okay, so let's go ahead and give these some names. E, A, we'll call this point right here C, call this one here D. I don't really need to name the center. But here's the thing. One of the things that we learned is that if you have a line that is tangent to a point on the circle, the angle created by the radius is going to be a right angle. Now, I know it doesn't quite look like a right angle, but assume that it is. So therefore, this radius is the same, this radius is the same, this radius is the same, and I'm going to call this length right here x and this one right here y. So we're going to do a little bit of Pythagorean theorem because this is a right triangle. Okay, so we have leg, so that's going to be x squared plus r squared equal to the whole hypotenuse. So the whole hypotenuse is going to be y plus r quantity squared. So now what's going to happen is that I'm going to go ahead and simplify the right-hand side. Okay, that's going to be y squared plus 2yr plus r squared. Now, if you notice, we have an r squared on both sides, so I'm going to subtract them. That gives me x squared equal to, now what I'm going to do here is I'm going to factor out a y. Okay, so then what I'm going to get is y plus 2r. So now let's think about what exactly does this mean. X right here, that's segment EA. Okay, y right here, that's segment EC. And y plus 2r, that is this segment. Y plus r, that's 2r. That is segment ED. Okay, hence now I have now derived basically the same formula. Okay, so it works for the case where it goes through the center. So EA quantity squared is equal to the product of EC times ED. Now let's investigate the case where the line does not go through that. Okay, so this one, probably a little more, not as complicated, but let's look at it. So you have E, you have A, you have point D, and you have point C right there. So what I'm going to do is I'm going to create a triangle going from here to here, and another triangle going from A to D. Now, one of the things that we have to look at is that this triangle right here, both triangles, they have the same common shared angle. Now, here's the part where it can get a little bit confusing, so I want to make sure I slow down on this one, okay? Because we did learn a theorem that states that the measure of angle EAC, that's this one, EAC was going to be half the arc of AC. So 1/2 the measure of arc AC. Okay, we learned that in one of the prior theorems. Now, because this right here, this is an intercepted arc, right? Not an arc, intercepted, yeah, arc, I want to say. Okay, to this angle right here, we have the measure of angle ADC equal to 1/2 the measure of arc AC. Now, voila, look at this. Aren't these two the same? Well, by the transitive property of equality, you are going to have the measure of angle EAC equal to the measure of angle ADC. Therefore, if those two angles are equal, they're going to be congruent, okay? So angle EAC is going to be congruent to angle ADC, okay? In other words, this angle right here is going to be congruent to this angle right there. Hence, now you have two similar triangles. Okay, let me zoom in a little bit on that so you can see it. Okay, you have two similar triangles. You have this one right here and the big one right here. So I'm going to go ahead and split it because I know it's a little difficult to see. So I'm going to go ahead and split the first one. I'm going to call this one here EAC. Okay, here and here. Okay, and I'm going to split the second one also. Okay, that's going to be E, A, and D. So now that I can actually split it, I can actually set up my proportion. So that's going to be EA. EA is to ED. And EC is to EA. So when I cross, that's EA. So when I cross multiply, I'm going to get EA squared equal to EC times ED. And you notice that I pretty much derived the same equation as the one right next to it. So as you can see, it kind of works both ways. Okay, whether this one right here goes through the center or if it doesn't go through the center. All right, we are ready now to start our examples. Okay, so don't forget, example 1 goes down here at the bottom, and examples 2, 3, and 4 go right there. And that's the extra practice, if you haven't noticed. All right, let's take a look at this first one here. On the first one here, we are going to be using the first theorem that we just showed, the segment of chords theorem. Okay, so this multiplied by this equals this multiplied by this. So we're going to have x plus 2 multiplied by x plus 1, and that's going to equal x times x plus 4. All right, algebra 1 time. Let's go ahead and multiply these. X plus 2 times x plus 1 is going to give me x squared plus 2x plus 1x plus 2. Basically, what the heck did I just do? I don't know if they still teach you guys that, but, you know, I learned FOIL method. First, outer, inner, last. You know that little parrot's peak? If you haven't heard of the parrot's peak in algebra, then I don't know. Maybe I'm too old. So x squared plus 4x. All right, so here's a cool thing. The x squared subtract out. Combine this, you have 3x plus 2 equals 4x. Subtract 3x, and you get 2 equals x. So boom, we found 2, but we are not done because they actually want me to go back and figure out what these are. So we know that mn is x plus 2, so that's easy. That's going to be 2 plus 2, which is 4. And jk is all of this. So that's the sum of x plus 4. Oh, wait, I didn't do that right. Well, I'm not done, actually, because they actually want me to find out what ml is. Okay, I should have paid a little more attention. Okay, so ml is basically, we still need to figure out what nl is. I could have just added them all. Going a little ahead of myself. So nl. Okay, that's just x plus 1, which is 2 plus 1, which is 3. So therefore, ml is just the sum of both of these, which is just 7. Okay, getting ahead of myself. All right, so for this one right here, it's going to be 2 plus 2 plus 4. That's going to be 8. So jk is going to be 8. See, always read the instructions, because I found mn instead of, the other one. All right, ladies and gentlemen, that's example number 1. Let's take a look at the next one. Okay, so on this one, we are going to be using the segment of secant theorem. All right, so it's going to be very simple. It's going to be 9 times the product of RQ. Now, RQ is the sum of 9 plus 11, which is 20. Now, I'm going to show that so that way people can see where I'm getting the number. And then 10 times 10 plus x. All right, so that's the same as 9 times 20. Go ahead and multiply that in there. That's 100 plus 10x. 9 times 20, that's 180. Equal to 100 plus 10x. Minus 100, minus 100. And you get 80 equal to 10x. Sorry, I got the sniffles. And x is equal to 8. Don't worry, it's not COVID. I got tested. All right, so x is equal to 8. And plus, I already had COVID. Who hasn't gotten COVID yet? If you're watching this video from the future, COVID is a virus that killed a lot of people in the years 2020 and 2022. Okay, just in case you see this video like 10 years from now and you're asking yourself, what the heck is COVID? All right. Example 3. Okay, for example 3, we are going to be using the segment of secant and tangent theorem. Okay, so we have RQ. RQ is going to be 16 quantity square equal to x multiplied by the whole distance. Okay, the whole distance RT. So that's going to be x plus 8. So as you can kind of see, we are going to run into a quadratic problem. All right, let's see if we can figure this out. Let me see how good my algebra skills are. Okay, so that is going to be 256 equal to x squared plus 8x. All right, so I'm going to subtract 256. Okay. So from here, we're going to look at what two numbers multiply to give me 256 and add up to 8. Okay, so if you look at, I've been looking for numbers that actually work for this, and guess what? There are none. Okay, it's not that I'm doing it wrong. It's just that we're going to have to do the quadratic formula. So if you do not remember the quadratic formula, okay, it's negative b plus or minus square root of b squared minus 4ac, all divided by 2a. Have you guys ever derived this equation? It's also pretty cool. All right, so let's go ahead and derive and actually find what this is. All right, so negative b, that is negative 8 plus or minus the square root of b squared. 8 squared minus 4 times a, which is 1 times c, which is negative 256, all divided by 2 times 1. All right. Negative 8 plus or minus. Now that's going to give me 64 plus, because that turns to addition. Okay, so 256 times 4, that is 1,024, all divided by 2. Okay, so that's negative 8 plus or minus. Okay, now 64 added to that. That is the square root of 1,088, all divided by 2. Okay, so what we're going to be doing now is, I know they simplified, but if we're going to be giving a decimal place, decimals, like, does it really matter? Okay, so we're going to have negative 8 plus or minus the square root of 1,088. And that is approximately 32 point, it's actually about, yeah, I guess 32.9. It's a good approximation, all divided by 2. So that means we need to look at two possible solutions. Negative 8 plus 32.9 divided by 2, and x is equal to negative 8 minus 32.9 divided by 2. But here's the thing, that's going to give me a negative value for x, and we know that is not a possible solution. So negative 8 plus, put that in calculator, negative 8 plus 32.9, enter, divided by 2 is going to give me about 12.45. Okay, so x is going to equal about 12.45, approximately. So why did we discard this answer? Because I knew this was going to give me a negative value, and we know we cannot have negative length ever, you know? All right, so here's example number 3 completely. All right, last example, example 4. Says find the radius of the aquarium in the tank. So I know it's kind of hard to see that diagram. Let me zoom in a little bit. So we're going to be using the same rule that we were using. All right, so 20 square is going to equal the product of CE, which is 8, multiplied by the whole distance right over here. So this will be 8 plus 2r. All right, so that is going to be 400 equal to 64 plus 16r. Take away 64, and you get 400 minus 64, which is 336 equal to 16r, divided by 16, and you get the radius equal to 21. All right, ladies and gentlemen, this concludes our video lesson for 10.6. Thank you for watching.